All right, one last little section here that we got to talk about for chapter 10. And these sections here on allylic halogenation are going to combine with what we're going to learn later on in chapter 8, I think in particular, when we talk about alkene reactions. But it's something that we want to talk about now because we want to kind of like sum up all the different reactions that we know are important and are going to be relevant to the future. So this is going to sound, so there's some words that are going to sound a little bit weird, but I'll explain it in the terms that you need to know for now, and then it'll all make sense uh, once we get through the alkene section later on. Okay, so remember that basically when we do a bromination and when we do hydrogen abstraction, whichever one has the weakest carbon-hydrogen bond, so the lowest bond dissociation energy, is going to be the one that undergoes the hydrogen abstraction first. So we also remember that uh, allylic radicals are the most stable, and so the allylic CH bond is going to be the weakest to hydrogen abstraction. So like, for example, when we look here, we've got a secondary carbon that's not allylic that has a bond dissociation energy of 402 kilojoules per mole. The vinylic carbon-hydrogen bond here, 444 kilojoules per mole, again, because this is an sp2 carbon-hydrogen sigma bond. And then finally, we have our allylic position. This allylic position is the weakest bond, the easiest to break, because it would form a stable allylic radical. And that's only 364 kilojoules per mole. So, like if we form this hydrogen abstraction, remember we get this resonance stabilized allylic radical. So that is going to be very stable. So like we would expect that if we do a bromination of this, if we just have the radical, we would expect to brominate specifically the allylic site first. So it should be specific for the allylic site as it is. Now, okay, this is where something we haven't covered yet, it comes into play. But basically, this is an alkene. I hope you agree with me on that. Alkenes can react with bromine to actually form a new carbon-bromine bond from here. And we'll talk about that mechanism later on this semester. But just so we know, basically, we can't mix this alkene with bromine and expect to get the allylic product because we're gonna form a new carbon-bromine bond. It's not going to be selective. It could form a carbon-bromine bond from either of these carbons here, or potentially both. So we have to consider that fact, basically. Like basically, we can't use bromine to brominate an allylic carbon. We have to use a stabilized bromine radical, and this is what we do. We use what's called N-bromosuccinimide. So succinimide is this structure here. It's basically this, where you've got your nitrogen stabilized in between two carbonyl groups in a 5-membered ring. This is stabilized by resonance because, as you can see, this is allylic in 2 directions. So it's an allylic radical in 2 different directions. So that's very stable, and that produces just the bromine radical. Now, the bromine radical is not what's reactive with the pi bond. It's only going to be useful for bromination. So sure enough, by using N-bromosuccinimide, which we're going to abbreviate as NBS, we can brominate specifically the allylic site. So what happens is basically you use the N-bromosuccinimide, we do our hydrogen abstraction, we get another radical. This Br2 can then further propagate. You do a halogen abstraction, and that produces your new allylic bromine there. Now, keeping in mind, if you have an asymmetric alkene, the mixture of products can form pretty significantly. Basically, what happens is the radical that forms can be delocalized. So we end up, for example, we use N-bromosuccinimide here. We would expect to form a radical here, but this radical here is in resonance with a radical on the far carbon here, right? So let me draw this out for you. Hopefully this makes sense. This is an allylic radical, right? So that means it can form a new pi bond here between carbons 2 and 3. And then this other electron goes over here, and that forms this radical here. So this radical can do halogen abstraction, or this radical can do halogen abstraction. So just keep in mind, it's not always specific. You can get a mixture of isomers with this if it's asymmetric. Okay. So yeah, so that's allylic halogenation. Now there's one last chapter or section here that we have to do. We're skipping ahead to 10:13. and this is about chlorination. I mentioned before chlorination, we're not going to use it too much, but it is useful to synthesize alkyl chlorides if there's only one possible product, right? So like if you take cyclohexane, there's only one type of carbon on cyclohexane. They're all equivalent to one another. So you chlorinate it and you just use a high excess of cyclohexane compared to the chlorine, and you're going to get the monochlorine cyclohexane. So you can do it that way. For all the reasons we talked about in the last video, it's not useful if you have more than one carbons that can be chlorinated. Now, on the other hand, bromination is slower, and so it's more selective. And so you can kind of predict where the bromine is going to go on a given alkane, right? Here we see that there's a tertiary site here, so we know that this is going to form the most stable radical. So we know that's the most likely site to be brominated. Yeah. So really what this reaction does is, and this is going to make more sense in the future as well, as I mentioned, this is the utility of this reaction. We're going to be using NBS from now until the end of next semester, right? Until you're totally done with organic chemistry. It basically is an easy way that you can put a bromine on a carbon, and you can figure out which way it is. And then once you have a bromine on a carbon, then you can do substitution reactions, you can do elimination reactions. That's stuff that we're going to talk about in the next chapter, chapter 7. Okay, so that's the utility here is we're going to be doing this a lot more than chlorination for sure. So here's our review. Now we haven't reviewed this one yet, but we remember allylic bromination, that's where we use NBS and light. And we know that we're going to specifically brominate the allylic site using NBS and light. And then we also have the bromination of alkanes, so no pi bonds, right? And we know that we're going to brominate specifically the most substituted carbon. So those are going to be the most important reactions here. Now just keep in mind, we haven't really talked about that yet. We're going to talk about that in the future, so don't worry about that just yet. Okay, all right, so make sure to get some more practice with the lecture exercise down below. Ask any questions that you have in the discussion, and I will talk to you soon. And we're going to move on to the next chapter right after this.